Maharaja Agrawal University, Baddi. The topic for my today's presentation is organometallic clusters. Before going to start with organometallic clusters, I would like to introduce you to the term cluster compounds. So according to F.A. Cotton, a finite group of metal atoms that are held together by bonds directly between metal atoms are known as cluster compounds. So whenever there is a direct metal-metal bond present in a group of metals, the compound will be known as cluster compound. Now talking about organometallic clusters. As we know, the term organometallic means there is a direct bond between metal and carbon atom. So in addition to a metal-carbon bond, there will be the presence of several metal atoms that are also linked together by direct metal-metal bonds, and such clusters are known as organometallic clusters. And they are considered to be the possible intermediates in many catalytic reactions. So these are very important compounds. Among these organometallic clusters, the most studied class is metal carbonyl clusters. In metal carbonyl clusters, the ligand is carbonyls, and we know carbonyls are neutral ligands. So metal carbonyl clusters are usually in the low oxidation states like in 0, +1, etc. These metal carbonyl clusters are basically divided into two categories. One is low nuclearity complexes and another is high nuclearity complexes. We will be discussing these one by one. Coming to low nuclearity carbonyl clusters. Low nuclearity carbonyl cluster means the number of metal atoms in these clusters will be equal to or less than 4. Okay. And the first metal carbonyl cluster which was studied was Mn2CO10. Now let us say there is a metal carbonyl cluster which contains 3 metal atoms. Now we do not know what kind of bonding is present in all the metal atoms, whether every metal atom is singly bonded to other metal atom or every metal atom is doubly bonded to other two metal atoms. So to calculate the number of bonds in the low nuclearity carbonyl clusters, there is a series of steps which we need to follow. So following steps are involved to calculate the number of bonds. Step 1 is to calculate the total valence electrons on central metal in the compounds. Now let us say we are talking about Mn2CO10 only. In this compound, the central metal atom is manganese. So the total number of valence electrons in manganese will be equal to its electron, will be calculated on the basis of its electronic configuration. Manganese has atomic number 25. So its electronic configuration is 4s2 3d 5. Okay, so the total number of valence electrons is 7 in manganese. So in this way, we calculate the total number of valence electrons in central metal atom and we denote it by A. Okay, now step 2 is the calculation of B. B is basically N into 18 minus A. Why we have taken this N into 18 in consideration? Because this is in accordance to your effective atomic number rule. Okay, we are taking the effective atomic number rule in consideration. If it follows the effective atomic number rule, the compound is said to be stable. So it does not need to form more metal-metal bonds. So on this basis, we calculate the value of B, where N represents the number of metal atoms in the compound. For example, in Mn2CO10, N will be equal to 2. There are 2 manganese that are present in your cluster compound. So N is basically the number of metal atoms that are present in a compound. Now step 3 is getting the value of B by 2. B by 2 gives the total number of bonds present in a compound, and the value of A by N gives the number of electrons per metal. Okay, if the value of A by N is 18, what does that mean? That means your compound has completely followed the effective atomic number rule and there is no need to form additional mm bond. So if the value of A by N comes to be 18, there will be no mm bond present in the compound. If the value of A by N is 17, then it is one short of 18. So we say that there will be presence of 1 mm bond per metal. If the value of A by N is 16, there will be 2 mm bonds per metal. If the value is 15, there will be 3 mm bonds per metal and so on. So we can follow this procedure to calculate the number of mm bonds present in low nuclearity carbonyl clusters and ultimately suggest or determine the structure of these compounds. Now we will be solving some examples to get a clear overview of these steps. First one is M2CO10. Here, M is manganese, technetium, or rhenium. So what was the first step? First step was to calculate the number of total valence electrons present in your compound. So there are two metal atoms and all have valence electrons 6. So we have taken the number of valence electron is 7. So we have taken 2 into 7 plus there are 10 ligands, carbonyl ligands attached to your compound. So every neutral ligand contribute 2 electrons. So it will provide 2 into 10 electrons. So total number of valence electrons would be 34. Okay, next step was to calculate B. B was N into 18 minus A. So N is 2 in this example. So we have 2 into 18 minus 34. That comes out to be 2. So what does B represent? B was representing your N into 18 minus A. We will be dividing it by 2 and this B by 2 will give us total number of mm bonds. So in M2CO10, total number of mm bonds is 1. Next thing was to calculate number of bonds per metal atom. That was given by A by N. So A was 34 and N is 2. So A by N is equal to 17. So it is 1 short of 18. So there is 1 mm bond per metal. So in this way, we can calculate the total number of mm bonds as well as number of mm bonds per metal. Next example is CO2-CO8. In CO2-CO8, central metal atom is cobalt. Cobalt has 9 valence electrons and there are 2 cobalts present in this cluster compound. So A is equal to 2 into 9 corresponding to 2 cobalt atoms plus there are 8 carbonyl ligands. So 2 into 8 for these ligands and we get the total number of valence electrons is equal to 34. So next we calculate B. B is N into 18 minus A. So we got B equal to 2. B by 2 will be equal to 1 again. So total number of mm bonds is equal to 1. Then A by N comes out to be 17. So there is 1 mm bond per metal. So on the basis of this information, we can determine the structure of the compounds. Like in CO2, CO8, we have 1 mm bond between cobalt-cobalt atom and thus we can predict the structure on basis of this information. All right. Next example is Fe2CO9. Again, there are 2 metal atoms. So obviously, total number of mm bonds will be equal to 1. And number of mm bond per metal atom will be equal to 1 again. And the structure is given on the basis of this information. And there is a bridge structure. There is a direct metal-metal bond present in the cluster compound. And there are 2 bridging carbonyl atoms and 7 terminal carbonyl ligands attached. Next one is Fe3CO12. Now there are 3 metal atoms. Now we cannot say that exactly just by looking at the formula that there will be number of mm bond 3 or 4 and how many Fe bonds per atom will be present. We have to calculate using the steps. First step was calculating the total number of valence electrons. So A is it comes out to be 3 into 8 because there are 3 iron atoms and each iron have 8 valence electron plus 12 into 2 for these 12 carbonyl ligands. It gives us total number of valence electrons to be 48. Next step is calculation of B. B comes out to be 6 and when we divide B by 2 we get 3. So the total number of bonds comes out to be 3. So we say that there are 3 metal-metal bonds present in our compound. Now next thing is to calculate number of Fe-Fe bonds per iron atom. When you divide A by 3 we get 16. So what does it tell us? It tells us number of Fe-Fe bonds per iron atom is 2. So on this basis, this structure was predicted. Okay, in this structure you can see each iron atom is bonded to 2 other iron atoms, and in totality there are 3 number of iron bonds. So we can use these formulas or steps to calculate the total number of metal atoms and number of metal atoms in the compound. Next example is IR4CO12. Now iridium has 9 valence electrons. So total number of valence electron will come out to be 4 into 9 plus 12 into 2, that is 60. Next step is calculation of B. B comes out to be 12. When you divide 12 by 2 we get 6. So total number of iridium 4CO12 compound is 6. There are total number of 6 metal bonds present in this compound. Okay, and when you divide A by N we get answer 15. So every iridium in this cluster compound is bonded to 3 other iridium atoms. Okay, so on basis of this information this structure was predicted. So these steps help us to predict the structure of your organometallic cluster compounds. Okay, next we will move to for square planar complexes. We know that for square planar complexes they follow 16 electron rule. They do not follow 18 electron rule. They follow 16 electron rule. Sorry. So we will follow the same steps. Just in place of 18 we will be using n into 16 to calculate B, and rest all the steps will be same. So in this way we can calculate the number of bonds in square planar complexes which obey 16 electron rule. Okay. Now next moving on to high nuclearity carbonyl clusters. What are high nuclearity carbonyl clusters? These are the compounds, cluster compounds, which contain more than or equal to 5 metal atoms in the cluster. Okay, the first high nuclearity carbonyl cluster compound to be discovered was rhodium-6 CO16. Okay, now we cannot predict the structure or calculate the number of bonds in high nuclearity carbonyl cluster like we did for low nuclearity carbonyl cluster, because these cluster compounds they follow your Wade's rule of your skeletal or framework electrons. So we will be following or using Wade's rule to calculate the total number of bonds. First thing is same, we will calculate the total electron count. Total electron count means we will be calculating the total number of electrons which are present in your cluster compounds. And if there is some interstitial atom present means, for example, you must have studied for boranes. Like if it is a closoborane, they have a particular structure and particular geometry. But interstitial means beside that cluster or skeleton, there are other atoms which are interstitially present in that skeleton. Those are interstitial atoms. Okay, so if there are certain interstitial atoms like hydrogen, carbon, nitrogen, phosphorus, etc. are present, we will be adding their valence electrons to the total electron count. Okay, for example, hydrogen has 1 valence electron, so we will be adding 1 to your TEC. Carbon has 4 valence electrons, so we will be adding 4 to your TEC and so on. Next, According to Wade's rule, each metal atom utilizes 12 electrons and each CO ligand utilizes 2 electrons irrespective of bonding, terminal or bridged for non-skeletal bonding. Okay, so whatever the type of ligand present, either it is terminal, it is bonding or present in the skeleton, it is fixed that each metal atom will utilize 12 electrons and each ligand will utilize 2 electrons. Okay. Next thing is calculation of polyhedral electron count. Polyhedral electron count will be equal to your total electron count minus n into 12. Why we have taken n into 12? Because we have considered that each metal atom utilizes 12 electron for skeletal bonding. So apart from those electrons, the other will be used in polyhedral electron count and as your total number of metal atoms. Next thing is we will be calculating PEC by 2, and on the basis of the values which we get after calculating PEC by 2, we predict the geometry of the compound. For example, if it comes out to be n minus 1, the geometry is supposed to be super closo. If PEC by 2 is equal to your number of metal atoms, that is n, then the geometry is hyper closo. If it is equal to n plus 1, geometry is closo, and so on. Okay, so on the basis of this method, we can calculate or predict the geometry of your high nuclearity carbonyl clusters. Okay, so for boranes, we were using this type of analogy. Okay, for closo we had total electron count equal to 4n plus 2. For nido we have total electron count equal to 4n plus 4. For arachno, total electron count is 4 and 6. For hypo, total electron count is 4n plus 8. So we can either predict the geometry on the basis of TEC, or we can predict the geometry on the basis of skeletal electron pairs. We can use both of them. Okay. Similarly, for transition metal clusters, the metal is another apart from boron. We will use this. 14n plus 2 represent closo, 14n plus 4 represent nido, 14n plus 6 represent arachno, and 14n plus 8 represent hypo. Now let us solve some example to get an idea how to predict the geometry of these high nuclearity carbonyl cluster. First one is RH6CO16. Okay, so there are 6 rhodium atoms present and 16 carbonyl ligands are there. So first step is calculation of total electron count. So total number of valence electron per rhodium is 9. So 6 rhodiums into 9. Okay, then there are 16 carbonyl ligands. So 16 into 2. So total electrons will be 86. So if you want to put it in terms of your 14n form, it comes out to be 14n plus 2. So geometry according to 14n plus 2 is closo. We can also predict it on the basis of polyhedral electron count. That was polyhedral electron count was your total electron count minus n into 12. So total electron count was 86 minus n into 12. N is 6. So it comes out to be 14. PEC by 2 gives us value 7. So that is in n plus 1 form. So the geometry is closo. So in this way, we can calculate the geometry excuse me, for a high nuclearity cluster compound. Similarly, next example is OS5CCO15. Now, here is an interstitial carbon atom present in this cluster compound. For osmium, total number of valence electrons are 8. So 5 into 8 plus 4 valence electrons of carbon plus 15 carbonyl compounds into 2. It gives us total electron count to be 74. And it comes out to be in form of 14n plus 4. That means geometry is nido. Also, we can predict it on the basis of polyhedral electron count. So it comes out to be 74 minus n into 12. That gives us 14. And if we divide 14 by 2, we get 7. So the number of metal atoms was 5. So it gives us n plus 2, that is nidogeometry. So in this way, we can predict the geometry. Another example would be ruthenium-6 CCO17. Here also one interstitial carbon atom is present, so we will be considering its valence electrons as well. So the number of valence electrons for ruthenium is 8. So 6 into 8 plus 4 for your valence electrons of carbon plus 17 carbonyl ligands will donate 17 into 2 electrons. So total we will be getting 86 valence electrons. 86 total electron counts, okay? So if we write it in form of 14n plus form, it comes out to be 14n plus 2. The geometry is closed. Also, we can calculate it using PEC. It comes out to be n plus 1 form, further suggesting the closure geometry. So in these way, we can predict the geometry of your high nuclearity carbonyl clusters. Okay, so we will be following these steps to calculate the geometries and total number of bonds and the number of bonds per metal atom for low nuclearity and high nuclearity cluster compounds. So that would be all for today's lecture.